So today we'll be looking at histogram, and this is used for quantitative variables with many values. This is usually used for continuous variables, and I'm not going to get into much into what a continuous variable is. We're going to look at it later, but a continuous variable is something that takes on a continuum of values, that takes on values in an interval. Okay, for example, the variable height, can take on any value, any positive value, right? So it takes on a value in an interval. So I'm going to explain how to make a histogram for a given data set through an example, and then I'm going to write down the general steps to follow to make a histogram. And I knew that OneNote will be stuck again, so alright, so let's look at this table. What I have in this table is the IQ test scores for 60 randomly chosen 5th grade students. And so all the values are there. These values are not in order, so they are not sorted. If you look at a table like this, it doesn't quite tell you much, right? Obviously. So once again, the need for summarizing, organizing the data is so that we can understand the data. Okay. So we are going to make a table, and the table will be called a frequency table, just like a table we made for a bar graph. A little bit different though. So we're going to make a table which is this table. This is called a frequency distribution table. So once you have the data, the first thing you want to do is count how many values you have in your data. Okay, how many data points. And if you count in our example, you get 60. So 60 is the number of data points. And then you want to figure out what's the minimum value in my data set. And the minimum value turns out to be 81. The maximum value in the data turns out to be 145. So the range is basically the maximum minus the minimum. So this is the range of values. So what's the range of values you have in the data? So what is 145 minus 81? Is that 64? Everybody's okay? Now, so now what we want to do is we want to divide the data into classes or groups. Okay? We want to divide the data into classes or groups. Now, how many classes would you like to pick? Well, if you want to divide it into classes, there is no hard and fast rule. There is a rule of thumb. The rule of thumb is you should use between 5 to 20 classes. So depending on your data size. Okay. So the number of classes will be somewhere between 5 to 20. Once you make a decision on how many classes you want, then you can figure out what should be the length of each class. Once again, when I say a class, it's like an interval. So I have the range of values from 81 up to 145. Think about the number line, 81 up to 145, right? And I want to divide that into subintervals. Is that making sense? So I decided in this case that I'm going to use 7 classes, and then I have to decide what should be the width of each class. Now notice that in order to figure out what should be the minimum length of a class, what should be the minimum width of a class, what you have to do is divide the range by the number of classes you picked. So if you divide 64 by 7, what do you get? I'm sorry? If you divide 64 by 7, what do you get? Seven times 9 is what? Yeah, so about 9, right? The length or width of the class should be about 9. But what did I pick? I picked 10. Why? Because 10 is a easier number to handle, right? 10 is more of a nicer number than 9. Okay? Now I'm going to write out my classes. When you write out your classes, all you have to make sure that you cover all the data points. You cover all the values in the data. So my minimum was 81, but then I decided to start at 80. And I decided to go from 80 to 90, 90 to 100, 100 to 110, and all I have to make sure that I'm going above, I am covering my maximum. So the last class here is 140 to 150. Is everybody clear? Now again, why did I pick the classes in this way? Because they are nicer numbers. I could have started at 81. I could have gone from 81 through 81 plus 9, which is 90. And then I could go from 90 to the 99 and so on if I wanted to. But, you don't have to be, you can pick your classes in a nice way like this. So once you have picked the classes, the end points of a class, are called the class boundaries. Is that making sense? The class boundaries are the end points of the class. So if you look at the third class here, the class boundaries are 100 and 110. 100 is called the left end point or the lower end point of the class. 110 is called the upper end or the right end point of the class. The third column I wrote down the upper bounds or the right end points of the classes. Frequency here, the frequencies that so what is the frequency of a class? The frequency of a class is the number of data values that lie in that class. Okay, so between 80 and 90, let's look at our data and see how many values we have between 80 and 90. So look through the data values. How many values do we have between 80 and 90? So there is 82, right? 82 here, 81 here. Where is 89? Bottom right. Oh, right here. Right, those are the three. I don't think there are any others. So the frequency of the class 80 to 90 is 3. There are 3 values falling in between 80 and 90. Yeah. 90 will fall into the second category. So you have to make a convention. You have to decide if you have a data value that is equal to one of the end points of a class, right? You have to then decide, does it fall in the Does it fall in the class with where it is the right endpoint, or does it fall in the class where it is the left endpoint? So the convention that I made here is it falls in the class where it is the left endpoint. Is that making sense? So 90 will fall between 90 and 100. So 90 will be counted as a member of the class between 90 and 100. That's the left endpoint, left-hand convention that I'm following here. You can also make a right-hand convention if you want to, but it doesn't really matter. But you have to pick a convention. You don't want to count 90 twice. Is that making sense? So if you have a data point, data value that is equal to an endpoint, then that data value belongs to the class where it is the left endpoint. Okay? Is everybody clear on that convention? So 90 is not counted as a member of the first class. 90 is counted as a member of the second class. Okay, so everybody understands what frequency means. So the frequency of a class means the number of, the count of how many values fall within that class. Right? Okay, once I have the frequencies, what should be the total frequency, anybody? What should be the total of the frequencies? 60, right? There is a total of 60 values, right? And relative frequency. So how do I come up with the relative frequency of a class? The relative frequency of a class is the frequency of the class divided by the total of the frequencies, or the total count, right? The total count was 60. So if I divide 3 by 60, I'm going to get 0.0500. So that's the relative frequency column. So I computed the relative frequencies for all the classes here. Is everybody clear on that? So what is the relative frequency then? The relative frequency is the proportion of values in the data that fall in the class, right? So the relative frequency of the first class is the proportion of values that belong to the first class, right? So these are the proportions. Everybody understands what a relative frequency is. Okay, so density, the column for density. Density is, I am dividing the density is equal to the relative frequency divided by the width of the class. Okay, so for the first class, the width is 10, right? And I'm going to divide the relative frequency by the width. So if I divide the relative frequency by the width, I am getting what? 0.005. Is everybody okay? So you're basically dividing the numbers in the relative frequency column by the class width. And remember, the class width was 10. So that's called the density of a class. So the density of a class is the relative frequency of the class divided by the width of the class. Cumulative frequency. Cumulative frequency of a class. The cumulative frequency of a class is the sum of the frequencies of classes up to that class and including that class. So which means if you look at the class between 80 and 90, the cumulative frequency for that is still 3 because there are no other classes before that. But if you look at the cumulative frequency for the second class, it is the frequency of the first class plus the frequency of the second class. If you look at the cumulative frequency for the third class, that's the frequency of the first plus the second plus the frequency of the third. Is that making sense? So the cumulative frequency of a class is the sum of the frequencies of the classes up to and containing that class. And of course, the cumulative relative frequency, once again, you are dividing, the cumulative relative frequency is basically, you are dividing the cumulative frequency by the total count. Or you can also say that you are, the cumulative relative frequency of a class is the sum of the relative frequencies of the classes up to and containing that class. What should be, can somebody tell me what should be the sum of the relative frequencies? 1, right? Total proportion should be 1. Total of the proportions should be 1. And of course, if you look at the last row of the cumulative relative frequency, and that's got to be 1 as well. Okay, because you're adding up the proportions, right? Does the 1 make sense to everybody in the last column, last row? Because you're adding up all the relative frequencies up to and including that class. Okay, so that's the frequency distribution table. To summarize, any questions on how I made that table? I used Excel to do that instead of doing it by hand. So it's easier if you know how to use Excel to do that. Okay. Once you have that, now you make a histogram. There are a couple of different histograms that I can make. I can make a frequency histogram. I can make a relative frequency histogram. I can make a density histogram. So what are they? Well, basically, to make a frequency histogram, so my second picture here is the frequency histogram. So basically you are drawing frequency versus scores, right? So along the horizontal axis, what you're doing is you're going to mark the class boundaries, right? So along the horizontal axis, you're marking the class marks are not shown here, but this should be, 80 to 90, 80 to 90, 90 to 100, and so on. So mark the class boundaries. Okay, now on each class, above each class, you want to make a rectangle with height equal to the frequency of the class. Is that making sense? So that's the frequency versus scores. That's called the frequency histogram. I can also make the relative frequency histogram. This is the relative frequency versus scores. So once again, along the horizontal axis, you are going to mark the class boundaries, and then above each class, you're going to make a rectangle with height equal to the relative frequency of that class. Everybody is okay? So remember, what is the relative frequency? Let's look at the table. What was the relative frequency of the class between 100 and 110? And that was 0.2667, right? And if you look at the class between 100 and 110, the height here has got to be 0.2667. Is that okay? All right, so we can also make a density histogram. The density histogram, once again, on the horizontal axis, you have to mark the class boundaries. And then, this time, above each class, you make a rectangle with height equal to the density of the class. Okay. So the heights of the rectangles here are given by the class densities. Is everybody clear on that? Now, one thing that I need you to realize is that the total area, the reason density histogram is important is that if you look at the total area of these rectangles, it's going to be 1. And let's see why. Can someone tell me what is the area, if you look at the first rectangle, if you look at the first rectangle, what's the area of that first rectangle? What's that? The area of that is 0.5. 0.5? Okay, so let's see the area of one of this rectangle, right? So area of a rectangle in this picture is equal to, well, it'll be width times the height, right? It'll be the width times the height. Now, what's the width? For all of them, the width is 10, right? So the width is the same for all of them. Let me just write width again. And what's the height for a density histogram? What's the height of it? What's the height? The height is the same as the density of the class, right? So what is the density of a class? What was the definition? The density of a class is the relative frequency of the class divided by the width of the class, right? Well, notice that what am I getting here? I'm getting the relative frequency, right? So that means the area of each rectangle is the same as the relative frequency of the corresponding class. Well, what's the total then? Well, the total is the total relative frequency, right? Which is 1. Is everybody okay with that? Everybody is convinced that the total area for the density histogram has got to be 1. So once again, the area of a rectangle in the density histogram is the same as width times the height, but the height is given by the density of the class, and the density of a class is the relative frequency divided by the width, and therefore the area of one of these rectangles is the relative frequency of the corresponding class. So if you take the total area of these rectangles, you get the total relative frequencies, total of the relative frequencies, which is 1. Okay, so let me know if you need time to write that down. Now, one thing you could do is print out the notes from Moodle and then bring them to the class, and then update those nodes as you need. That's going to make it easier. At least the pictures are there. All right, so if you're okay with that, let me give you an example. So remember that example. Maybe I can go back to that example for a second. So we had this So look at, remember that for each of the 50 states, we had the percent of the percent of Hispanic population, right? So there were 50 numbers in our data, and we made a stem plot for that before. We can also make a histogram for this. And so basically, on the horizontal axis, so if you look at all the values, so we are looking at the size of the Hispanic population, the percent of Hispanic population, right? And it goes from 0 up to 45. So you divided your data into how many classes here? 1, 2, 3, 4, 5, 6, 7, 8, 9 classes here. And the width of each class is 5. Okay. So notice that the height of the first class is probably 27 or 28. Let's say 27. So what does it mean? There are 27 states where the percent of Hispanic population is between 0 and 5%, right? So there are, if you look at this class between 20 and 25, right, the height of the rectangle is what? 0, right? So that means there are no states having where the percent Hispanic population is between 20 and 25, right? Same thing for between 35 and 40, and then you see that there is exactly one state. I think that the height of that rectangle is 1. There is exactly one state where the percent of Hispanic population is between 40 and 45%, right? And that was, remember, that was exactly New Mexico, right? There is 42.1%. 42.1% of the population there is Hispanic. Once you collect the data, then if you have a value that doesn't fall within the overall pattern of the data, it's called an outlier. Whenever you have an outlier, you ask yourself, is that because of a typing mistake? Is that because of a mistake done during the data collection process and so on? Or if it is real, correct, can I explain why that's the case? Okay, so I don't know, I haven't looked up exactly the historical reason why we have a big percent of Hispanic population in New Mexico, but if you know historical reasons for that, then you can explain why that's the case. Everybody understands what an outlier is. Okay. All right, so remember density histogram. So when I am talking about fitted smooth curves in histograms, assume that all the histograms are density histograms. What's the one of the properties then is that the sum of the areas of the rectangles in the histogram is what? 1. So once you have a histogram, you can fit a smooth curve through the histogram that approximates the overall pattern of the histogram. Okay? So that's called a density curve. A density curve is a smooth curve that approximates the overall shape of the distribution. Let me know if you need time to write that down. Okay. I looked at some of the discussion that many of you had on the discussion board in Moodle, and there were some questions about the right tail of a histogram, the left tail of a histogram. So once we fit a smooth curve, then we can talk about the shape of that curve. So the right tail of a histogram means what? The right tail of a histogram is basically the right of center side of the histogram, right? So this is the side with the large values, right? The right tail of a histogram is the right of center side of the histogram. Left tail means the left of center of this. Left of center side of the histogram. What is a symmetric distribution? Symmetric distribution means that the right tail is approximately mirror image of the left tail. Okay. Are this clear to you? So when the right tail is about the same as the left tail, yeah, go ahead.
Is that the same as being skewed left or right?
Yeah, I'm gonna get there in a second. Yeah. So the skewed to the right means the right tail is long. Skewed to the left means the left tail is long. So when you have a symmetric distribution, my first picture has an example of a symmetric distribution. So this is approximately symmetric. And if you look at the other picture, that's a skewed distribution. So what is a skewed distribution? It's something that's not symmetric. Okay. Once again, well, we talked about this outlier thing. Did anybody have any questions on the on outliers? Okay. When you have an outlier, what's the first question you ask yourself? Is that a typo? made a mistake collecting the data, right? Things like that. And if you think that it is real, if you think that's real, then can I explain why that's real? Okay, some people had questions on unimodal, bimodal distributions, right? Unimodal distribution means it's a distribution with one peak, and almost all distributions are unimodal. Bimodal distribution has two peaks, so this is there are some, but not that common. And multimodal distributions, these are distributions with more than two peaks, and these are rare. So if I show you the pictures of these distributions, they will pretty much tell you what we mean. So unimodal means you have just one peak, right? So the first picture that I have, that's unimodal. The second picture has two peaks, so that's bimodal. And the last one has multiple peaks, so that's a multimodal distribution. Skewed distributions. So if you look at these two pictures, that pretty much tells you what's the meaning of right skewed and left skewed. So the right skewed means what? The right tail is relatively longer than the left tail. Left skewed, the left tail is relatively longer than the right tail. Now notice that when you look at the first picture, notice that the bulk of the values are on the left. In the other one, the bulk of the values are on the right. Okay. The reason we can say that is because, remember, we are looking at frequencies here, right? If you think of them in terms of the histograms, most of the frequencies will be on the right for this picture, right? For the second picture, most of the frequencies will be on the right. Symmetric distribution, in terms of the fitted smooth curves, it can look like one or the other, right? Symmetric simply means right tail is about the same as the left tail. Okay. One thing that I do want to point out here is that when you have a exactly symmetric distribution, the value corresponding to the highest point on the curve is the mean. This point here is the mean. Okay. Same thing here. Okay, so let's summarize what we have done. So how do we construct a frequency distribution table? Well, the first thing you do is choose a range of values that captures all of the data. In order to have an idea of the range of values of the data, what do? You look at the minimum value, the maximum value, and subtract, right? That tells you about the range of values. Divided into non-overlapping intervals. So divide the range of values into non-overlapping intervals, usually of equal length. Each interval is called a class, or a class interval, the endpoints of each class are called the class boundaries. The rule of thumb is there should be about 5 to 20 intervals. This is just a rule of thumb, so also use integers for the class boundaries if you can, and choose suitably simple intervals. Okay, so remember, I picked my intervals in length I chose the intervals from 90 to 100, right? Sorry, 80 to 90, 90 to 100, right? In lengths of 10, right? I could have picked, the lengths to be 8 or 9 or some other numbers, okay? Or 11 or 12, right? I just picked something that's going to look nicer, or looks easier to work with. Okay, so you want your intervals to look simple. So for example, use 10 to 20, 20 to 13, not 20 to 13 there, 20 to 30 there, sorry, there is a typo here, 20 to 30. Instead of using, numbers like 13.823 to 18.456, 18.457 to 27.538, and so on. Am I making sense? Use the left endpoint convention. If an observation equals an endpoint, then it belongs to the class with that observation as its left endpoint. So when I say the observation, I mean a data value. Okay? So an observation is a data value. And then a value in the sample. Number 4, calculate the frequencies of the classes. So the class frequency, or just the frequency of the class, is the number of observations or data values that belong to that class. Okay. The relative frequency, right? The relative frequency of a class is the proportion of observations belonging to the class. So it is the ratio of the frequency of the class to the total of the frequency, or the total count. What is the cumulative frequency? The cumulative frequency for a class is the sum of the frequencies of all classes up to and including the class. Right? The cumulative frequency for a class is the sum of the frequencies of all classes up to and including the class. Number 7, the cumulative relative frequency. The cumulative relative frequency for a class is the sum of the relative frequencies of all classes up to and including the class. And the last one, the density or height of the class, is the ratio of its relative frequency to the class width. Is everybody okay with that? How we construct a histogram. The first thing we do is we tick mark the class boundaries on the horizontal axis. We tick mark the frequencies or the densities for a density histogram on the vertical axis, and then we draw a rectangle above each class with height equal to its frequency or density. So Okay, we'll be looking at another diagram called ogive curve, but let me restart my OneNote again. That'll be the recurring theme of the class, that I'm going to restart OneNote again and again. All right, so okay, so remember when we created that frequency distribution table, there were two columns that I didn't use when that we didn't use in creating the histogram. So I have the cumulative frequency and the cumulative relative frequency. Those are the last two columns, right? And we are going to create a diagram using those two columns, and it will be called a ogive curve. So here's a diagram here. So what I have here is the following. So I have the along the horizontal axis, notice that at each, so 100, 110 up to 150, these are the upper bounds of the class boundaries, right? These are the upper bounds of the classes. Now at each upper bound, above each upper bound, I have a dot, right? And the height of that dot is the cumulative frequency, of the class with that upper bound. Okay, so for example, let me go back to the table again. So the first upper bound, wait a minute, why I have okay, I think when I created this diagram, I might not have picked the first one. That's why it's starting at 100. But okay, so the cumulative frequency with the upper bound 100 was 5, right? No, not 5, sorry. 8. Does that match what I have here? Oh, okay, I see where the mistake is. Okay, the mistake is that the first dot should correspond to 90, okay, and the last dot should correspond to 150. So I have to sort of indent the number upper bounds to the right. Okay. All right. So what I'm saying, this should really be 90 here, and here this should be 150. Okay. Is that making sense? So I have a typo in my picture. So for the upper bound 90, so if you go back again, the upper bound 90 right here, and then the relative, the cumulative frequency is 3 for the when you have the upper bound 100, right? So we are looking at this class here. The cumulative frequency is 8, right? So that's what we are plotting. The upper we are plotting cumulative frequency versus upper bound. And if I do that, that's the I get those dots, and then I connected those dots with straight line segments. Okay. Is everybody clear how I got this picture? Okay, now this one isn't as revealing as the other one. So instead of using the cumulative frequency, let's use the cumulative relative frequency. So again, it's the same thing. Now I have the correct numbers in my horizontal axis. So if I use the cumulative relative frequency, so for the upper bound 90, I have, I guess, let's look up some of the numbers again. I had 0.05, 0.133, right? So that's what I have here. The height of the point at 90 is 0.05, and then the height of the point at 100 is 0.13, and so on. So let's pick one. So let's think about what this is saying. So this height here, right, at 120. What is it saying? It's saying that a little bit above 60% of the values, 60% of the values are at or below 120, right? Is that making sense? So this graph is telling me the following. If I look at the height at 120, that's a little bit above 60, right? At 0.6. So what this is saying is a little more than 60% of the values are below 120. Is that right? Same thing here at 150, right? 100%, right? 100% of the values are below 150. Remember, 150 was the highest value in the data. Not the highest value necessarily. I mean, 150 is the upper bound of the last class. So obviously all the values are below 150. So then this is telling me 100% of the values are below 150. Did that make sense? So now, I can sort of approximate this connected line segments with a smooth curve, okay? And that's called the ogive curve. And if you just for a second imagine that this is a smooth curve, then even if I pick a value between 110 and 120, let's say 115, and if I look at the height of the curve at 115, whatever the height is and whatever the corresponding number is on the vertical axis, I don't know, let's say it's 0.5, just for the sake of the discussion. Let's say it's the height here is 0.5. Well, then that would mean that the 50% of the values are below 115, right? Approximately. Is everybody clear what this diagram is telling us? All right, so that's the end of the discussion on histograms.